Thank you, Anwar. So I will talk about inelastic scattering, and not only scattering, also infrared absorption, which is quite different than inelastic scattering, but I will tell you in more detail next. So first, I would be just to apologize because my Spanish is very bad. So I will make this course in English, but my English is not so good either. So it's better for you because then I don't have a very huge vocabulary, so it will be understandable for you. So I have 3 slots in this eNano courses. One today, one tomorrow afternoon, and one on Wednesday morning. And basically, the 3 slots are the 3 parts here of the talk. Here, part 1, 2, and 3. Here, basically, maybe can be moved a little bit, but basically is this. So the first part is a more difficult one. It's really theoretical, because to understand why light scatters in media, what was the basics of the interaction between the radiations and the media, one has to first describe some mathematical concepts in the scattering process. And so that's the aim of this first part here. So I will tell you about the linear response theory. And this part is documented by courses of Professor Courtens, who I benefited, and he gave this course in Master in Montpellier. And so I will first introduce some mathematical background needed to work the scattering experiment, towards the theory of the scattering experiment. So this corresponds to, for example, definition of the correlation functions, the susceptibility, whatever is the susceptibility, mechanical, electric, magnetic, and so on. That's a general concept which applies to everything, every vibration excitations. And finally, I will finish with the fluctuation spectra. Fluctuation spectra is exactly what you measure when you make an experiment. The second part will be devoted into experimental apparatus. And so here we'll go to more applications. So it will, the second part here is devoted on how works the experimental that probe the vibrations. And I will talk about mainly infrared absorption, neutron scattering, and Raman scattering. And finally, in my third course, I will give you something more fashion, something which is how we can work the spectroscopy to gain information on the vibrations, but at the end, the structure of the materials. Because the aim of the spectroscopy mainly is to gain information on the structure. Because sometimes the structural tools that you can use, for example, X-ray scattering, if you make elastic X-ray scattering, for example, that's what you have been told this morning. For example, you can gain information, but some of this information are completely averaged, and you can't access. By the usual structural tools. And so, inelastic scattering provides an indirect way to access some structural information. So that's very powerful. And the other thing is that inelastic scattering, for example, Raman on infrared absorption, is really easy to operate. So everybody has a Raman spectra, infrared spectra in his laboratory, and to characterize the materials, it's very easy tools. And so that's why it's quite interesting to know how it works. Okay, but why it is necessary to have some mathematical background is because we are working mainly in reciprocal space. So it's not direct information as you can get when you are doing, for example, AFM. That's you have heard about this morning. So in AFM, you have information in time and space directly. But then, when you make inelastic experiment or scattering in general, what you have is information in the Fourier space. I mean, you have information in the frequency and Q space, Q being the wave vector of the excitations. And so, what happens is that you have information because the experimental setups make itself a Fourier transform of what happened in the real space. Imagine you have a vibration, two atoms moving. If you can see them, you will see them moving, but with the apparatus, the scattering experiment apparatus, what you see is you probe its frequency, not its motion in time. You just make the Fourier transform to probe its frequency. So that's something which is not direct either. Okay, so this requires some mathematical background. So I will start this with this mathematical background. So sorry, it will be some equations, but I will try to be very slow to that purpose. So I will now concentrate on the linear response theory, so the first part, giving you first some mathematical background about the Fourier transforms of a quantity. Okay, let's introduce the Fourier transform. Fourier transform just make the transformation between real space and reciprocal space, or at the reverse, between reciprocal space and real space. So if you have a quantity r on t, which is r, for example, is a position vector, it's in meters, and t is in seconds. If you make the Fourier transform, then you transform this quantity into the reciprocal space, say that now you have the variables are q, which is a wave vector, which is 2 pi over lambda, which lambda is the wavelength of the radiation, for example, and the frequency omega. So you see, it's really the inverse of the quantity in real space. Say here you have meters and second. In reciprocal space, you have meter minus 1 and second minus 1. Second minus 1 is just hertz, the frequencies. Okay? So how it works? For example, if you have a quantity, small f of t, here, and you want to perform its Fourier transform, so the Fourier transform of f of t is large F, capital F of omega, which is this expression, which is an integral of the function f of t times an exponential, complex exponential. So this is the definition. And if you can do the reverse, say if you have capital F of omega, you can extract f of t by doing the reverse Fourier transform, which is exactly the same, but you replace plus I omega t by minus I omega t. And you integrate over omega instead of integrating over t here. And so what you have here is, if you do such things, what you get is information about the dynamical property of the materials. Because all these relate to time and frequency. There's two Fourier transforms. And so here you can get information about the relaxations and the vibration in the material. But you can do also, you can also perform Fourier transform in space. And in space you have this. So the Fourier transform of the function f of the position vector r is f of q here, and this is a triple integral because there are tri-dimensions in space, and this triple integral is written there, and then it's the function small f of r times a complex exponential of I q scalar r, okay? And the reverse Fourier transform is given there. So if you try to get the Fourier transform of f of q, this is small f of r, and this is given here. And here, what you get there is you access to static properties. For example, if there is order in the materials, and so on, if it's crystallized crystal, or if it is disordered material. When you have Bragg peaks, you work in reciprocal space. Okay? Yeah. If you have the interatomic distances, for example, A, the distances between an atom 1 and an atom 2, this is real space. If you make the Fourier transform of these distances, that you get the Bragg peaks. That's exactly this. Okay? If you have a function f of r, which is just the position of each atoms periodically placed into the lattice, you make the Fourier transform of this, and you get f of q, which is exactly what your experiment gives you when you make Bragg diffraction, for example. Okay? Okay, so in general, this is, if you combine this, you have a fourth order integral with time and spatial components. Okay, so I will, okay, these are the definition. We'll use it very weak, very few, but you have to have that. Maybe in the future we will need this definition. Okay, another function which is of really big importance is a Dirac function. Maybe you have already heard about that. I don't know exactly where you come from. But this Dirac function is just a function which is 1 at x equals 0 and 0 everywhere else. That's just there is just one value which is not equal to 0 in the delta function, and this value is 1 for x equals 0. This is a direct function. And now, this direct function has some properties. For example, if you integrate the direct function from minus infinite to plus infinite, that's the first here, the value is 1. Okay, this is easy to understand. And because if you integrate over all x, running from minus infinite to plus infinite, then the only non-zero value is at 0, and the amplitude is 1. So the integral is equal to 1. This is trivial. And now, if you multiply delta by a function f of x, whatever f of x, you understand that as delta is non-zero exactly at x equals 0, the result of this integration is just f of 0. Okay? This is another property of the direct function. And then you can also have a direct function which is not 0 at x equals 0, but a direct function which is not 1 at x equals 0, but 1 at x equals x0 here. Okay, that's just a translation. And if you do that, you will understand that as delta here is 1 exactly at x equals x0 and 0 everywhere else, so the integral of delta times f is just f of x0. Okay, this is also something which should be rather simple. Okay, and then we can try to calculate the Fourier transform of every kind of delta function. For example, I give you here the results for 4 types of delta function. For example, you have a delta function, the Fourier transform of delta of omega minus omega 0. This is the result, exponential of minus I omega 0 t, and so on. You have 4 of these expressions there, which can be used when you have to calculate the Fourier spectrum. We will see that after. Okay, let's check this one, for example. I will not demonstrate all, but let's try to demonstrate this one. This is really easy. The Fourier transform of delta omega minus omega 0, by definition, is this. Okay? And this is a Fourier transform of a function in frequency space. It gives a function in times. Okay? That's exactly the definition of a Fourier transform. Okay? But then, as far as delta omega minus omega 0 is not null exactly at omega 0, then this integrals is different to 0 only for omega equal to omega 0, and f of t then is equal to e to exponential e minus I omega 0 t. Okay? As you understand, that's the only non-zero value of omega which gives the only value, of omega which give a non-zero results is omega equal omega 0 there. Okay? So this is this, and then if I combine this and this, I find this result, which is exactly, what I gave you there. Okay? So you can try to work this for the 3 others. It's not, it's the same. It's not more complicated than that. Okay. Now, another example. Let's imagine a sine wave of frequency omega 0. Okay? This is, for example, atomic vibration. For example, a spring. You have the motion of a spring. Okay? And it gives you a sine wave. Imagine it's not dense, so it's an infinite sine wave. Or it can also be an electric field. If you generate an electric field, for example, light, laser light, is a sine wave. The field is a sine wave. So you have the sine wave here, and so this the function in time of this sine wave in a complex is exponential minus I omega 0 t. Okay, that's a complex form of this sine wave. And if you make now the Fourier transform, okay, I skip the detail here, but the Fourier transform f, capital F of omega, it's this expression here. And then if you run that till the end, you find, with the definition of I gave you from the direct function, you find that the Fourier transform of a sine wave is just a delta function. Okay? If the sine wave has a frequency of omega 0, then the delta function is not null exactly at omega 0. That's the only non-zero value of the delta function. Okay? So let's just say that the Fourier transform of a sine wave is a delta function at the same frequency than the frequency of the sine wave. Okay? That you have to remind this because this is quite important for the following. And so now, if you look at f of t, the sine wave in the real space. So it's a cos omega 0 t, okay? That's a real part of this expression there. And so that's just a cosine of omega 0 t. And you can write that in terms of exponentials, imaginary exponentials, okay, like that. And so you have 2 times this, what I've shown you before. And if you make the Fourier transform of this f of t, you find now that the Fourier transform is the sum of 2 delta functions, one at plus omega 0 and the second one at minus omega 0. Okay? So if you have a real sine wave, if you work it in a real notations, then the results, it's not just a delta function, but it's 2 delta functions, one at minus omega 0 and the other one at plus omega 0. Okay? And so to summarize this, you have this. If you have this sine wave at frequency omega 0 in time space, here, that's the time space, sorry, I forgot to, the x-axis is time, and this is the amplitude, for example. And so if you make the Fourier transform, what you find, if you find 2 Dirac peaks at minus omega 0 and plus omega 0. And this should remind you what you observe experimentally, for example, when you measure the excitation. Maybe you have already done that. Okay? This is exactly what you see when you measure excitations. You see a series of peaks at omega I, omega I 1, omega 2, omega 3, and so on. Okay? And that's exactly what you measure. Okay, that's enough for the background math. And so let's now go to a concept which is much more general than light scattering or scattering experiment. It applies to every fluctuating quantities. They can be mechanical, they can be I don't know, atoms, whatever, temperature, pressure. It applies to everything. That's a very general theory. Okay, so it's the point is to try to understand to get the response function of a media to an external perturbation. So we assume that the media is close to equilibrium. That's so the scale of the theory, okay? The framework of the theory is to assume that we are close to the equilibrium. It's not strongly out of equilibrium. And so it's linear. So the response to a perturbation, the response of a quantity to a perturbation it's proportional to the perturbation. And so that means that we have weak perturbation. That's the framework of this theory. Okay, and so the definition, which is very important, we work on that all over the discourse, is that if you measure the spontaneous fluctuation of a physical quantity, whatever the fluctuating variable, it gives a similar response than the same variable. It gives a similar response than an external force that coupled with that physical quantity. So that means that you have 2 ways to measure the response function of a variable. First, you measure the fluctuations. Okay, you have for example a gas. You have a gas, and you have a membrane, and you measure the displacement of the membrane. And this gives you the variation of the motion of the particle in the gas. Okay, you measure these fluctuations. Okay, that's the first thing. And this fluctuation spectra is exactly similar as if you irradiate this gas by incident waves, and you measure the response. Okay, there are 2 ways to measure the response function of material. First, you measure its fluctuations. Second, you use a laser, you use neutron, you use infrared radiations, and you measure the response. That's the same. That's 2 ways to do the same thing. Okay? Okay. And so, to understand this theory, we have to define first what is the impulsional response function of a media. Imagine the easiest example is a spring, because the spring is a vibration, gives a vibration which are really similar to what you have in solid, liquid, and gases as atomic vibrations. Okay, so let's consider a spring, and imagine that the spring is subjected to a direct force. That's a force which has an amplitude at t equals 0. Okay, you apply to this spring a force here, which has an amplitude of 1 or whatever at t equals 0, and it is 0 everywhere else. So that's you take a hammer, and boom, you bump the mass here, okay, very quickly. so that gives you a direct force. Okay, and this gives you, you know all that when you do that to a spring, what you expect is a damped harmonic, is a damped sign function as the equation of motion of the spring here. Okay, so the x of t, which is simply the displacement of the spring, as a damped sign, is a damped sign function. Okay, so this x of t here is just the impulsional response function of the spring. Okay, this is what we call the impulsional response function, saying that is a response to a direct force. Okay, so that's also easy to understand this concept. The second thing we have to define is a susceptibility key. Okay. So what is the susceptibility? Again, the susceptibility is not necessarily the electrical susceptibility. It can be the magnetic susceptibility, the mechanical susceptibility, it can be whatever you want. And the susceptibility is just the sensitivity of a variable to an external excitation. It says how the media will react to the perturbation. If the media will react very strong, or if it will react very, very weak. Okay, that's the susceptibility. The name is speaking. Okay, the definition of the susceptibility is just a kind of Fourier transform of the impulsional response function. Okay, this is this. The susceptibility, whatever the susceptibility you want to measure, is just the Fourier transform. Okay, so a kind of, because there should not be 2 pi there, but it's a kind of Fourier transform of the impulsional response function. So this is the way it works. And you see here that if the variable does not couple with the perturbation, that means that the impulsional response function will be 0. Okay, if there's no coupling, I take an hammer and I bump into a mass, and if the mass is very tough, then it will not move, and then the impulsional response function is almost 0. Okay, and then if the impulsional response function is 0, the susceptibility is 0. Okay, so that gives you an idea of what is the susceptibility. The way the quantity you are measuring is sensitive to the perturbation. And so, what you have to remind is that the susceptibility is proportional to the Fourier transform of the impulsional response function. That's something that we have to remind. And you can do the reverse. That if you know the susceptibility, you can get the impulsional response function of a system. Okay? Okay, so what are the properties of the susceptibility? First, imagine that you have a quantity x of t, you make the Fourier transform, and then you have capital X of omega. Okay? If you have the force, an external force, f of t, then the Fourier transform gives you capital F of omega, which is the internal force, while x of omega is just the response function. And then you have a relation, I will not demonstrate that, but we could, but we have a relation between the displacement x of omega, the susceptibility, and the force. Okay, that's linear theory, so that's a linear relation. And then you know that because if you remind, for example, if you have an applied electric field, this applied electric field will modulate the polarization of the media, and this modulation is doing so through this expression epsilon 0 times alpha, and this product is just the electrical susceptibility you know. That you have P equal to chi times E. Okay, this is what you have. And if you would consider magnetic systems, so here you would have the magnetic susceptibility instead of the electrical susceptibility. So you know that you have learned that, I think, that you can relate the external electric field to the electrical polarization in the media through a quantity which is just the susceptibility. This is much more general than in solid. Okay? So this is it. And so a second property of the susceptibility is that chi is complex in general. So chi is equal to chi prime plus I, chi double prime here. Okay? And if you remind, here you have, sorry, I come back here, you have this expression. Yes, you have, sorry, this expression, okay? And so if I replace chi with its expression and cosine and sine functions, I get this expression here. Okay? So chi is just an integral of the impulsional response function times a cosine plus a complex here term, which is the impulsional response function times the sine of omega t here. And so from that, you can see that the real part, as far as the impulsional response function is real, it's a real quantity, because the hammer is real. When you bump a mass with a hammer, the hammer is not an imaginary system, it's real. Okay? So as far as phi of t is real, then chi prime is even because the cosine is even. Okay, that's an even function. Chi prime is an even function because the cosine is an even function. And chi double prime, it's an odd function because the sine is an odd function. So that's give you some property of the real and imaginary part of the susceptibility. So chi prime is even, and it's called the active part, meaning that chi moves in phase with the applied external force. Okay? And chi double prime is odd, meaning that it is out of phase with the external applied force, and this is what we call the reactive part. Okay? And let's take another example. Still the spring. Chi prime in the spring, you have a spring here, and then you have a viscous force, and you have also the force from the spring. You have an external force, and so you have the velocity of the spring, which is like this here. Okay? And so chi prime is in phase with the applied force F, and so it relates to the stiffness K. Okay? That's the active part. What makes the spring moving? It's stiffness K. Okay, that's the stiffness K which makes the spring moving. But on the contrary, chi double prime is out of phase and it stops the motion. It hinders the motion. Okay, it has a way to stop the motion because it's completely out of phase from the displacement. Okay, so chi double prime relates to the viscous force and it relates to the friction coefficient gamma. Okay? So if you measure the susceptibility, for example, in solids, what you will have, if you have an experimental tool which measures the susceptibility, the real part will give you an information about the strength of two neighboring atoms, for example, while the imaginary part of the susceptibility will give you information about how the motion wants to stop, the viscosity, for example, of the motion. Is related to the imaginary part of the susceptibility. Okay? Okay. The third property of the susceptibility is what is called the Kramers-Kronig relations. It has been derived in 1927, so that's about one century ago. And it says that there exists a relation between the real and imaginary part of the susceptibility. And this relation at this one, okay, I give you this just for information. That you will compile this, you will have this forever after, and you can use it if you make an infrared spectroscopy. You can take this back in a few years, and you can use this formula. For the moment, I will not go into detail of that, but I just want to emphasize that what is very strong in these relations is that a measure, if you measure just the real part of the susceptibility, you can access the imaginary part and vice versa. Okay, that's very interesting. For example, if you measure a transmission spectra in infrared, what we do usually, you measure transmission spectra of materials, then you access here to the imaginary part exactly. Okay, and then using the Kramers-Kronig relations, you don't have to measure chi prime by making a reflectivity spectra. You just have chi prime just using these expressions. Okay, so that's very, very important expressions. One disadvantage or difficulty is that if you want to apply this, you see that you have to integrate from 0 to infinite. And the problem is that usually instruments never measure from 0 to infinite. So that's So that the problem of this expressions is that when you get one quantity from the other, you need to have really extended spectra from at least highest value as possible. Okay, so that's the problem. And so for our purpose, these Kramer's configurations are really important, for example, in infrared absorption. They are commonly used in that spectroscopy to analyze data. Okay. Okay. Let's go now. I have defined the impulsional response function, the susceptibility, and now I have to define the fluctuation spectra. Okay. Let's consider a media which is isolated. But even though it is isolated, you know that things are moving inside, just because of thermal energy. Okay? The atoms are always moving, except when you put that at zero, absolute zero temperature. But even there, they are still moving a little bit. But at a given temperature, you have always the energy, which is K times the temperature, which is given to the material, and that the material is always moving. Okay? And then you can measure the average value of a quantity A, for example, and you know these definitions, that the average of A, which is bracket of A, average in time, for example, it's a limit when capital T tend to the infinite of 1 over T integral of T0 to T0 plus T, A of T dt. T0 being the time you start the experiment. Okay? I measure something, and the time I start the experiment is at T0. Okay? But it's the same. This quantity is the same as this. You say that you translate the time scale, and you say, okay, T0 is 0, and you change T0 from 0, and so these two expressions are identical. Okay, so now what happened? I measure the fluctuation. Okay, there's no external force there. Okay, I just measure the fluctuation of a quantity in time here. Okay, so that the quantity is A, whatever is A, and so I measure, for example, the amplitude of A versus time, and what happened? What I find is something like this. Okay, that's a fluctuation spectra like that. Okay, and in general, you will agree that A of T is different to A of T plus tau, which tau is a difference here between times. But there can exist correlations between the different value of A you are measuring in time here. For example, when if you are at small tau value, if you measure at T and just a T prime with very close to T, you will understand that you have something, the system reminds what happened just few seconds before. Okay, so you have a correlation with what happened in T plus tau with what happened at T when tau is very small. Okay, but then you lose this correlation when time is increasing. Okay, and if I measure, for example, a quantity at time T, I come back 2 hours later, and maybe there will be no correlation at all with the two quantities I measure. Okay, so this says that we can define what is called an autocorrelation function. And so the autocorrelation function, the definition is G of tau, which is just the average of A of T plus tau. Okay? And if you look back the definition of the average of A, this is exactly the same, but I replaced A of T by A of T times A of T plus tau. Okay? That's exactly the same. Okay? And so there are some property of G. G has some properties. So, sorry. For example, there is time invariance. I already told you about that just before. So that if I measure at 0, if the origin of time is 0, so at 0 A of tau average is the same as A of T plus tau is equal to G of tau. That's all. This is the same because you just translate the time. Okay, and then the integral is with capital T tend to infinite, then it is the same. Okay, then another property, if tau tend to 0, exactly what I told you just before is that A of T plus tau tend to A of T. Okay, because there is strong correlation between what you measure at the time and what you measure at the time just after. Okay, the system remember what happened just few instants before. And so what this here translates into the relation that you have average of A of T. This is just the average of A squared. Okay. This is the greatest, the largest value you can have. And average of A squared is always greater than this, because you can't have larger correlations than A squared. If tau tends to infinite, as I told you before, there's no correlations between A of t and A of t plus tau. And then, if you look at this limit of the correlation functions, so there's two variables that are completely decorrelated, so you can separate the average, and you have average of A of t times average of A of t plus tau, and this is average of A squared. Okay? So in the first limit, you have A squared average, and here you have average of A squared. Okay? That's all for that. Okay, so now let's apply that to a physical system. I want to measure the autocorrelation function. For example, if I look to a scattering by a solution of polystyrene spheres. You have polystyrene spheres in solution, so they are all moving along owing to the Brownian motions. Okay, and then you irradiate your sample here by a light source, for example, a laser, and you look at the scattering in a given direction there. Okay, and you assume that the laser is so weak that it does not perturbate the medium. Okay, there's no perturbation because the laser is very weak. You just have few energy laser. Okay, and so what you get here, if you measure the scattering, is a noise spectra of the system. Okay, and you always see that. And if you smoke in an area with a laser, you always see some particles lightning. Okay, and so that's something which relates to that. And if you measure the scattering of this, so you have the scattering intensity here versus T, and you have a noise spectra exactly similar to what I showed you before. And if you put that in a correlator which is just a software which calculates the correlation function I gave you before, and what you find, if you find the correlator here, the correlator calculates G of omega, which is that, and what you find, if you find something which is the dots here, okay? What you are calculating there is the product of I of t times I of t plus tau, and you make tau varying from 0 to infinite. Okay, that's what you do. And so what you measure when tau is increasing is this, and the value at 0 here at 0 time here is exactly I square average, and the value at infinite, tau tends to infinite, is exactly what I told you before, is I average square. Okay, the dots are the experiments that have been calculated with this correlator through the experimental value which are there, and the line here is a fit, and you can fit this with an exponential. Oh, sorry, I forgot the minus there. Okay. There is a minus. So exponential minus tau over 2,0. Okay, so what you can fit this point by a function which is just given there, where you have an exponential decay with tau 0 being the relaxation time of the particles. Okay, and what does that mean? That means that I have a solution of moving particles. They are moving because of thermal motions. Okay, I measure their scattering. I measure their fluctuation spectra, the fluctuation of the scattering. I make this correlation function, this here, I repeat, this is the correlation function calculated by the software, and I can get, what I get is an exponential decay which is exactly this form. I repeat that here there is a minus there, okay? And tau is a relaxational time, and it relates to the diffusion coefficient, which is a physical quantity which is interesting to know in liquids. Okay? So you see that just by measuring the fluctuation spectra, I have access to physical quantities. Let's take another example. Now I just take two atoms connecting by a spring, and x of t is the displacement, which is the two atoms, and I measure here the fluctuation. I have a way, there's no way to do that, but I have a way to measure the fluctuation spectra of these two atoms there, and I got exactly the same as before. That's a noise spectra where x is just here, x is just the displacement, x of t there. I forgot to put that here. That's x of t here. And I've got a notch spectra. I put that in a correlator. And the correlator calculates the autocorrelation function of this quantity. And what I get is this. That's completely different. Now what I get is in the damped sign motions, where the ordinate at the origin here is x squared average. And if I feed this with a function, I can feed that with a damped cosine here. And so this quantity can be fitted with this function. So you have the amplitude. Okay? So the amplitude there gives you the maximum displacement, amplitude displacement of the atoms. Gamma here is just the damping, okay? Which relates in a real space to the relaxation time of the motion. Say that imagine that you bump on this system here, and gamma relates to the time the system comes back to its equilibrium. And then the third quantity you have is the frequency, the normal frequency of the motion, which is just square root of k over m, where k is the stiffness of the spring and m the mass of the atom there. Okay? Okay, so just by measuring the fluctuation spectra, the fluctuations of a quantity, you get its response. Okay, this is the autocorrelation function. But now what we need is a fluctuation spectra. The fluctuation spectra means that you need, spectra means a quantity in frequency space. Okay? Autocorrelation function is in real space, that's time, and now the fluctuation spectra is a quantity which is related to the frequency space. Okay? And so the definition is this, is that the fluctuation spectra is just the Fourier transform of the autocorrelation function. That's really simple. And so this is this. Okay? And the interesting point there is that S of omega is exactly what you are measuring by an experiment. Exactly this. You are measuring, I tell you that today, but I will tell you that many times during these 3 days. You are measuring what you are performing an experiment. You are measuring the Fourier transform of the autocorrelation spectra, of the autocorrelation function of the quantity which couples to the excitations. Something which is complicated, but then you have to get rid of that. You have radiations. The radiation coupled with a quantity. For example, in X-ray, the quantity which coupled to the radiation is the electronic density of the atoms. Okay. In light, it is the polarizations, the electrical polarizations. Okay. So you have radiations. This radiation couples to a physical quantity, and your spectra measure the Fourier transform of the autocorrelation function of this quantity. Okay. That's what you are doing experimentally. Okay. Okay, so just to give you examples that are far from condensed matter physics, this concept are used by many people and engineers. And for example, if you want to build a bridge, for example, you have to monitor the bridge, and you have to know how the bridge responds to the vibration, and you have to perform what we call the bridge signature. Okay. You have a nice bridge here. I took a nice photo, I think, on the web. And so you can measure, okay, there's no car on the bridge. You put on this bridge, after you have constricted it, you put an accelerometer on that bridge. And if you do that, you measure the accelerometer, we measure the displacement of the bridge, which is fluctuate due to the wind, for example, due to the water outside, due to anything you want. Pressure variation and so on, air pressure variation and so on. Okay, so you measure this, and what you measure the noise function, the noise of the bridge, the displacements in time, and this is this. Okay, this is the displacement. Here they are in volts. Maybe it's too small there, but they are in volts because you measure the tension. The apparatus measures the tension. Also, that's the displacement. Of the fluctuation in time, so that's second here. Okay, so you measure that. This really looks nothing. I mean, just you can't say anything about this. Okay? But then you put that information, this spectra, in a correlator, which calculates the tension times the tension after a time tau. Okay? That is a correlation function. You perform the Fourier transform, and what you get is a power spectrum that is the fluctuation spectra, and that's similar. The fluctuation spectra of the bridge. And the fluctuation spectra is in volt square because it is in intensity. Okay, that's a spectra that's in intensity, so in volt square. And what you find here, so that's volt square here, versus now it's in frequency, because we Fourier transform the time response. So that's hertz. And you find here that it's almost flat. Okay, it's almost flat. There is almost no response, except at about 2 hertz, where there is resonance. Okay? Okay? So what you expect is this. When you construct a bridge, you expect that the spectrum is almost flat. Because if not, what happens is this. If your bridge have resonance at low frequency, say at frequency which are similar to the moving cars on the bridge, for example, or if the frequency are similar to the typical frequency of winds on motor and so on, then what happens? You will enter in resonance and the bridge can break. Okay? So that's really an example of how people measure the fluctuation spectra of a quantity. You understand that for a bridge, it's impossible to put a laser on it. Okay? You will not irradiate the bridge with a laser. That's a very huge piece of art, so you can do that. Okay? And though there are also many other possibilities to use this linear response theory in general application. For example, in buildings, typically, just to prevent earthquake, you have to build buildings whose resonant frequency are very far to the frequency, typical frequency of the earthquake, and so on. Okay. Okay, I close this parenthesis, which was just to tell you that these concepts are much larger than just condensed matter physics. Okay, let's come back to the fluctuation spectra. Now, the last but not least things we have to define is how to relate the susceptibility you can access experimentally and the fluctuation spectra. And this is given by what is called the fluctuation dissipation theorem, which is just the relation between S of omega, which is a fluctuation spectra or power spectra, and chi double prime, which is the imaginary part of the susceptibility. You can relate these two things, which is simple formula. This is a classical expression here. It works for bridges, for example. For bridges, for buildings, it works. Okay. But for phonons, it does not work because phonons are controlled by quantum mechanics things, and for excitations, the quantum theory tells that S of omega, so the fluctuation spectra, relate to the imaginary part of the susceptibility through this expression, that's the H bar over omega, and this is N of omega, which is the Bose-Einstein population factor, which is defined there. Okay? That's the quantity of quantum excitation which are in the system. Okay? And you know, maybe you know that when you go to low temperature, the materials are frozen in, so there are less excitations, and so N decreases strongly when temperature is decreasing. Okay? And N is also decreasing when frequency is increasing. Okay? So you can plot, if on a computer, you can plot this, and you will see how N of omega behave, M of omega being the number of phonons you have. Okay? Okay. Okay, let's come back now to the real example. I would like to calculate now the susceptibility of a vibration. Let's take back the spring, because that's ideal case that's really easy to work on. So, for example, I take this spring. So same as before, I have this spring here, which have an external force there. You have a viscous force here, which in opposite direction of the external force, And so the equation of motion is this one. You may know that. I'm sure you have already seen that. M is the mass of the mass here. Gamma is the viscous constant. K is the stiffness of the spring. And F is the external force. Okay, if you go to in Fourier space, so the external force of F of t become F of omega E minus I omega t. X is X of omega, capital X of omega, and some exponential function. Okay, and then the equation of motion become that. I replace what I did here. I just replace X of t. That's X of t. I replace X of t there by capital X of omega times E times this exponential function. Okay, just I did that there. And F, I replace F, small f by capital F by this expression. And I got that. Okay? And now, if you remind that the susceptibility relates to the displacement through this expression, I already show you that. Okay? I can find here, okay, I have X, capital F, so I can find the susceptibility chi, which is there, here. That's the imaginary expression of the susceptibility. And if I take the real part, the imaginary part of that, I found chi double prime, which is this. Okay? So this is the imaginary part of the susceptibility for a vibration. Okay? That is its expression. And here you have gamma, omega 0, and so on, and chi 0, which are given there. Okay? You can do that on your own. This is really easy. I think this is quite easy. It's always written. There's only 1 or 2 lines missing. Okay, and so what is this? This here. Okay, you remind that this is just what we need in this expression. I am measuring experimentally. I am measuring S of omega, and now I found an expression of K double prime. Okay, this, and so S, the fluctuation spectra or power spectra, given that is the spectral response given by the spectrometer, okay, is this. If you have a vibration, if you measure a vibration with a spectrometer, what you will find, the spectrum you will get, it's exactly, this for example, and these two lines can be fitted by this expression. And this expression is what we call a damped harmonic oscillator. Okay? So in every inelastic scattering spectroscopy, you measure phonons. Phonons are what you can see there, everywhere here. Okay, here. Okay. And the line, the point are the experimental data, and the line are just a fit with this expression. Okay. So we did all the work here. Okay, we start from the basics, and we found exactly what you are measuring experimentally. Okay. So as I told you, so the inelastic response of a material gives information of the atomic excitations. That's the motion of atoms. Okay, and this provides an indirect way to probe first the structure, because the atomic excitation mimics the structure of the solid. Okay, so you can directly relate what you are measuring in the dynamic, the dynamic you are measuring to the structure of the solid. Okay, and then you can access the dielectric properties, you can access the magnetic properties, you can access elastic properties just by measuring the excitation in the solid. So that provides really interesting tools to gain access to the physical quantity in solids, liquid, and gases. Okay. Okay. So, how does that work experimentally? Okay, so a scattering experiment. So the principle is the following. So you have a source here, for example, a laser, a neutron source if you are doing neutron scattering, an infrared source if you are doing infrared absorption, and so on. No, sorry. Forgot about the infrared, because infrared is not a scattering experiment, okay? So you have a neutron source, a light source, laser source, electrons source, and so on. So you have this source, you have a monochromator which selects the frequency and the incident wave vector here, Ki. You irradiate your sample, and then you look at the light scatter in a given direction, for example, in that direction, that's completely arbitrary here. And this defines the scattered wave vector, Ks, and the analyzer will select the frequency you choose within all the scatter frequency. Okay? And then you have a detector. Okay? And so, first is that a scattering experiment needs to fulfill energy and momentum conservation laws. That's the first step. Okay? And so that's what we call the kinematic conditions. And so, first you have energy conservation. So imagine you have an incident, let's say a light source, a wave, a laser source, at a frequency, incident frequency omega I, and incident wave vector Ki. Okay? You irradiate a molecule like that. And so what you can do, if the molecule is not moving at that moment, you can induce a motion, a vibration in the molecule, that is what is schematized there. So you have a vibration h bar omega, and then the scattered light has changed its energy. That is inelastic scattering, because the scattered energy is different to the incoming energy, because you have given some energy to the molecule there. Okay? And the energy conservation law writes h bar omega s equal to h bar omega I minus what you have given to the system, which is h bar omega, omega being just the frequency of the motion you induced in the material, in the molecule. Okay? So you have this. And this is what we call a Stokes process. And in a Stokes process, you have created a phonon. Okay? There was no phonon there. There is a phonon here, a vibration. And so the population factor of this Stokes process is n of omega. You remember n of omega is a Bose-Einstein population factor. So you have, and this is the population factor for a Stokes process is n plus 1. Okay? That's the population factor. Another type of process is that now I have exactly the same incident energy there, okay, with frequency omega I and wave vector Ki, and then here the vibration is moving, is fluctuating, is vibrating, okay, and what this process can do is to cancel or to annihilate this vibration, and then from something which was vibrating, you have at the end something which is not vibrating anymore, okay. So then in that case, the scattering wave vector, the scattering frequency omega s is different also to the incoming energy, but then now omega s is greater to the incoming energy, because the incoming energy plus the energy of the vibrations give the scattered photon, for example. Okay? So the energy conservation law now is h bar omega s equal to h bar omega I plus h bar omega. And the population factor of such process is n of omega. And you will see that here now, that when you have a Stokes process, the population factor is n plus 1. When you have an anti-Stokes process, the population factor, so the quantity of vibrating of phonons, n of omega is, the population factor is the quantity of vibrating units. So how many phonons you have is n plus 1. Okay? And sorry, for such a process, which is called an anti-Stokes process. Okay? And you see that this one is greater than this one, and the explanation is really simple, is that it is always possible to create a phonon, but to annihilate a phonon, the phonon first needs to exist. Okay? So the probability, if you look in quantum mechanics, the probability to annihilate a phonon is smaller than the probability to create it. Because at every temperature, the molecule can be frozen, okay? And so you can always create a phonon. But to annihilate it, the phonon has to exist already. Okay? So that gives you, these two lines here, give you the two possible processes for energy conservation. Okay? The second conservation law is momentum conservation, and so that's a conservation of the wave vectors. So you have the incident wave vector, the scattered wave vector here. Okay, let's now talk about Ks and Ki, and you have a triangle that you have to close by the difference of these two wave vectors. Say that Q, which is a scattering wave vector, that's the wave vector at which you are looking at, which is plus or minus Ks minus Ki. Okay, and this is the conservation of the momentum. You need to have that in a scattering experiment. Okay, and theta here, theta is what we call the scattering angle of the experiment. Okay, so finally you have these two expressions there. That's omega s equal to omega I plus or minus omega. This comes from that. Okay, that's energy conservation. And Ks equal to Ki plus or minus Q, which is the momentum conservation. Okay, and so now let's come back to the scattering experiment with these two conditions. I just draw again this scheme. And what you have at the detector, if you plot here omega s, okay, and in the abscissa it's omega s, the scattering frequency, and here in the y-axis it's just the intensity, the scattered intensity. What you find is when omega s is exactly equal to omega I, you find usually a big line, which is just what we call elastic scattering. The elastic scattering is when the scattered frequency energy is equal to the incoming energy. Okay, it's what you do when you do X-ray scattering diffraction, for example. X-ray diffraction. X-ray diffraction is an elastic spectroscopy. Okay, because the outgoing energy is the same as the incoming energy. Okay, so this is this line. Okay, which is very large. And for example, if you are doing light scattering experiment, this line is what we call the Rayleigh scattering. Maybe you have heard of that. This line is a Rayleigh scattering, and the Rayleigh scattering is the elastic part of the scattering of light. Okay, and it's usually much stronger than the inelastic part. Okay, so let's continue. When now you are doing your spectra with frequency omega s, which is different to omega I, you have two types of contributions. First, you have here contributions in both sides, which are really similar. They are exactly at the same frequencies. The only differences are the amplitudes, okay, which are different on the left from the right side. Okay, let's consider that here you have at outgoing energy, which are smaller than the incoming energy. Omega s here is smaller than omega I, and so you are considering, you are dealing with Stokes process. Create an excitation, and as I told you, the population factor is n plus 1, means that it's greater than n, the population of an anti-Stokes process. Okay, and that's why these lines on the Stokes side are higher than the line on the anti-Stokes side. That's because the Stokes process has a higher populations than the anti-Stokes process. Okay, and here we can check that we are really on the anti-Stokes process. Omega s is greater than omega I, meaning that you have cancelled annihilate a vibration, and the energy of this vibration has been given to the outgoing beam. Okay, so this is what you get when you do an elastic scattering experiment. Okay, so now I can come back. Okay, let's see. Sorry. Okay, now I can come back to what we did before. Okay, remember this spectra. See, the spectra is exactly similar to this one, for example. Okay, this you have the zero energy there, you have the Stokes or anti-Stokes, I don't know, frequencies there on the other side. Okay, okay, you have the two companions of the same vibration, and the two companions from the same vibration there. Okay, here again. You see here it's obvious that this is the Stokes side and this is the anti-Stokes side, because here the energy, the level is higher than that. Okay, so you have a phonon there, a phonon here, the zero which gives you the Bragg scattering, okay, the elastic scattering, and you have two phonons, okay? And this one is greater than this one, meaning that here you have on the stock side, okay? You have this. And let's now come back to what I told you at the very beginning. This. What did your experiment? He did that. Okay? Life is this. The experiment gives you that. This is life in time and space quantities, if you want. This is real life, and this is Fourier transform life. Okay? And this is exactly what you have. So now, okay, I give you this idea. Maybe at the beginning you did not have the spirit on where I want like you to go, but now you have the answer. I give you the answer, and now you can come back and try to understand in more detail exactly what I told you during this seminar. And I told you just at the beginning, this is the answer of 1 hour and a half talking. Okay, this is just the answer of all the talk. Okay. Okay, so how many time? Okay, so I have time, so I can start. So the second part. Okay, so I will skip now the real theoretical things, and I go now to the experiments. And so I will talk about experiments which probe the atomic excitation. I did not say scattering experiment because infrared is not a scattering experiment. Infrared is absorption spectroscopy. It's not scattering. Okay, so that's why I did not say here scattering experiment. So I will introduce first on molecular excitation. What are molecular excitations? Then I will give you some input about the origin of the infrared absorption. I will talk about neutron scattering, maybe not today, and Raman scattering, probably tomorrow. Okay? Okay, so what was maybe not really clear before, I hope will become more clear now. So you have two types of excitations. You have relaxations, which are characterized by relaxation times. Relaxations are, for example, you have, okay, let's consider the example I gave you before, for example, the polystyrene spheres in a liquid. Okay, if I move, if I take one sphere, I move it from its equilibrium, and then it will go back it will move again. Okay, so this is a relaxation time. Imagine you have a molecule in a system. I move it from its equilibrium position, and I leave it free, and then the molecule will come back to its position, but in a specific time scale. Okay, this is relaxation, and relaxation is different to vibration. In vibrations, if I move a molecule from its equilibrium position and I release and I leave it free, then the molecule, instead of going back to its equilibrium, it will vibrate like that. Okay, so that's different. Okay, that vibrate, and at the end it will come back to its equilibrium position, but then it vibrates. So that's two different type of motions: vibrations, which are motions around an equilibrium positions, and relaxations, which can be, for example, the Brownian motion. Brownian motion, if you the polystyrene spheres, they move like in a random walk, and this is defined by the relaxation time. That's something which relates to the speed of the balls. Okay, so you have two types of vibration: relaxation, excitation, relaxation, and vibrations. And so, in vibrations, you have also two types of vibrations. For the first one are the local molecular ones. Okay, so let's consider a condensed material. Okay, you have molecules, large amount of molecules, and then one molecule is doing something like that, breathing, for example. Okay, and then the other, few angstrom away, does not see this motion. Okay, so the other moves also because of the thermal energy, but there's no phase relationship between the two molecules. If I take one and I move it like that, the other one does not hear anything, does not see anything, and she just moves as she wants. Okay? So there's no phase relationships. That's what we call local vibrations. And in case of local vibrations, you have no wave vector dependence of the frequency, and this gives you here, if you look at that, which is a dispersion curve. So I plot here the frequency of the vibrations as a function of the wave vector q, which is just, I remind you, 2 pi over lambda. Okay? If I plot that, this local molecular vibration gives an almost flat dispersion curve, saying that I can look at every scale. I will see exactly the same frequency. And then, on the contrary to that, you have collective motions. Collective motions are motions which induce a lot of particles. For example, you have a chain of spring of atoms at the nodes of every of the springs, and then you move one atom at the beginning, and you release it, and then the motion will propagate all through the chain. Okay? And this is a collective motion because every atom, even if they are far from the first one, they at one time they will know what happened to the first one. Okay? Okay, so that's collective motion. For example, sound waves are collective motion. When I'm talking to you, this is a collective motion. Okay? The atoms are moving like that. I make with my mouse, I make some move of the atom. They are moving like that. And there are density fluctuation, and this density fluctuation come to you here, and you hear me, okay? And it's a collective motion, because the atoms which are very close to your ear, at one time they will know that I have produced a certain frequency, okay? So that's completely collective, okay? And though these collective motions are different to the other one, if I plot the dispersion curve of this collective motion here in the dispersion diagram there, this looks like that, and they are called acoustic branches. And the acoustic waves that you know what is a sound wave, for example, of a material, is given just to tell you that, is given by the slope of these lines at q equal to 0. Okay, the slope here, omega over q, gives you the speed of sound in the material. So this has acoustic branches. Acoustic branches are typically collective modes, and there's a strong wave vector dependence for these modes. Okay. Okay. Let's come back now to the local vibrations. There's one. There is a way to discriminate all the local vibration in a media, and this way is what we call normal modes. So maybe you have heard about that. You can, okay, if you take a molecule. Because of the thermal energy, the molecule is moving everywhere, in every sense, in every direction, all the time. Okay, and so you can't characterize the vibration like that because it's moving randomly. So you need a basis as the Cartesian basis. You need a basis to analyze the vibration. And what you do is you define normal modes, and the spirit of that is to say that every motion of a molecule is just a linear combination of all the normal modes you have defined. Okay? So let's take, for example, this planar triangular molecule here. You have an atom, blue one here, and a red one at the center here. And so you can define, okay, this molecule is moving in every direction every time. Okay? And if you want to describe the motion, you can define the normal modes. For example, you can define one motion, which is just a breathing motion here, where the molecule, the atoms, the blue atoms are moving in phase, back and forth, and that's a breathing mode. You can define shear modes like that of the molecule. Okay, shear mode in the plane, shear mode here out of plane, says the molecule moves perpendicular to the plane of the slide here. You can define other modes, okay? And then the interest of this is that once you have defined the eigenmodes, all the eigenmodes, in these basics, for example, for this kind of molecule, you have, say, 6 eigenmodes, not more. Okay, it's not an infinite. You have, okay, for this you have 5 or 6 eigenmodes. All the motion of the molecule here, whatever it is just a linear combination of this motion plus this one, plus this one, plus this one, etc. Okay? And so that's something which is very interesting, because then if you just the motion of a molecule is just characterized by its normal mode, and it's really easier than to define a motion in general. Okay. Okay, so I just repeat a little bit what I've told you before here. You have different types of vibrational spectroscopy. You have light spectroscopy, infrared absorption, Raman and hyper-Raman scattering. I will tell you a little bit about that in my third talk, I think. Brillouin scattering, inelastic neutron scattering, inelastic X-ray scattering. For these two here, you need to go close to a reactor, a nuclear reactor. So you have, usually it's not in a laboratory, it's a service laboratory. That's large instruments. For example, in Europe, we have several. You have one in France, which is a new European center, and then every European countries come there to make their experiments. So that's a very large facility, very big facilities. You can also do inelastic X-ray scattering, and for that you need a synchrotron. So you can go close to a synchrotron and make experiments, and to see the vibration probed by inelastic X-ray scattering. Okay, so you have a very wide panel of spectroscopy, and you would say, but okay, that's nice, but why so much spectroscopy? Just one would be enough. But no, because as I told you, each variable couples more or less with the radiations. Okay, that means that if you, for example, if you want to study light, let's say X-ray scattering, because I know you have a course, you had a courses in the morning. Let's take X-ray scattering. As X-ray scattering is sensitive to the electronic density of the atoms. Okay, that's rho, the electronic density. And so what you measure in X-ray scattering is the correlation function of the Fourier transform of the correlation function of the electronic density of the atoms. But now, if you have a material which has very light atoms, hydrogen, for example, you will never see any X-ray signal, because it's so light that it will not couple with the X-rays, because you have just one electron. Okay? If you want to study lead, if you want to study lead, if you want to study lead, that's okay, that's fine. But if you want to study hydrogen, it's not good. So if you want to study the vibration in hydrogen, it's better to go to neutron scattering, because hydrogen has a very large, okay, let's say, incurrent scattering lengths, and then it's very good for the hydrogen materials in neutron scattering. Okay, and because it couples very efficiently. And for light scattering, it's the same. For example, I will show you that after, that if you perform infrared absorption, you will probe just one part of the vibration, because there are like these selection holes, and then not all the vibration can be observed by infrared absorption, which you see just one part of the vibrations. In Raman, the other part. In hyper-Raman, another one, etc. And it is just the sum of all the spectroscopy which gives you the full signature, vibrational signature of your material. Okay, so that's why one spectroscopy is usually not enough. Okay? You need to do several. What do we measure with inelastic scattering? We measure the frequency of the excitations. Okay, this is just a summary of what I've told you before. You measure the frequency of the excitations, their intensity, very important if you want to analyze the selection rules. For example, if you want to know if one excitation is sensitive to infrared light or not, you need to know what is its intensity in infrared. Okay, so that's very important for selection rule analysis, the intensity. You also get the bandwidth, if the phonon is damped or not. This is also an important information. You can also measure the polarization property of light, for example. For example, you have a material, you enter into a material with a radiation which is polarized, so you have a light polarized vertically, for example. You enter through the materials, and after, the light is polarized, not vertically, but in another direction. Okay? Okay, so you can measure that. And you can obviously measure all this quantity with the temperature, pressure, electric field, and so on. And what is important there is what you can access. And the inelastic spectroscopy provide, for example, information about the crystal symmetry. I have a signature, a vibrational signature of my system, or by playing with the selection rules, I can access the group symmetry of my, for example, if it's a crystal, I can access the space group of the crystal just by measuring the vibrations. Okay, so that's another way to measure the symmetry of the materials. You can do Bragg diffraction. That is the easiest. Okay, but sometimes when you do Bragg diffractions, you have an information which is average. Yeah, you have an average structure which is okay given by the Bragg diffraction. But if you want to look into details of the structure, then the vibration is much more sensitive. Okay, and this is very powerful. For example, it's disordered materials. For example, you have an average structure which is cubic, crystalline average structure which is cubic, but imagine that now the atom that's slightly off center, okay, in a random way. You will never see that in Bragg diffraction, okay, because you have in average the atoms are at their equilibrium position, but then if you look one atom by one, you see that there are some distortions, okay, and so you will have very nice Bragg peaks, although the structure at local scale is disordered. And the only way to probe that is looking at the vibrations, because vibrations are very sensitive to local disorder. Okay? And so you can access this. You can also access to phase transition. For example, if you measure phonons with temperature, pressure, or electric field, dopant concentration, and so on, the phonon will be affected by the change of structure. For example, the frequency, if you decrease the temperature of a crystal which is cubic at high temperature and becomes tetragonal at lower temperature. Okay? You make Bragg diffraction, you see growing different peaks because you have a transition. So the Bragg diffraction will tell you that you have changed the structure. But the vibration also, because the vibration are sensitive, obviously, to the structure in which they are vibrating. So you can access also phase transition by doing inelastic scattering. You can access the symmetry of a molecule in liquids. You can access local and medium range structure in glasses. That's also in glasses and in disordered systems. That's also very important because that's medium range structure is somehow very difficult to access by structural tools. And so, as inelastic scattering is very sensitive to local behavior arrangements, then you can access information that's completely impossible to access otherwise. Okay. You can access also elastic properties. Okay, Young modulus, Poisson modulus, by doing Brillouin scattering and many other information. Okay, so there are many things you can access by doing inelastic spectroscopy. And one advantage of that is that they are usually, for example, for this, the elastic properties, you can access the elastic property by performing mechanical tests to your sample. You apply a force and you see the response, and you have the Young modulus. Okay. But then the interest of that is that it's non-destructive. That Brillouin scattering, you irradiate your material with the laser light, and you measure the vibration, and you have the elastic. You get the elastic constant, and then your modulus like that. So that's very interesting. For example, to get elastic properties of media that you can touch. For example, in fiber optics, you have fibers. You melt the fibers, and you want to see what is the elastic property of the fibers in the melt. Okay, it's 1,000 degrees Celsius, and you don't want to touch it. Okay, and then you can do that just by doing Brillouin scattering. You can say the viscosity here is this, the elastic constant is that, and so on. Okay, so that's something sometimes which is very useful because it's non-destructive, and you can do that at distance. Okay. Okay. I think I will stop there, if you don't mind, because then I think that's enough. I've spent 1 hour and a half, and I think that's enough not to lose you completely. And then I think I will stop, and just to tell you, tomorrow I will give you information about infrared radiation neutron scattering and Raman scattering. I will tell you in detail how it works. I will give you how to work with the selection rules. I will give you a little bit of practicals just for Raman scattering, how to apply the selection rules and so on. There will be some exercises and so on. Okay, and in the third talk, I will give you real application, research application of all these techniques. So I thank you for your attention today. So if there are any questions, here are the places you can answer. One thing, if I think I forgot to put here my website, not my mail address. So if you don't want to ask questions now, if you have some other, I'm here for the 3 days. But then you could also after send me emails, and I can try to answer. Okay. Okay. So, are there any question here? No question. Can you ask if there are maybe? Can you ask them if there are? Huh? I don't even know if they hear me. So okay, no questions? Check your hand if not. No, I don't know. Okay, so thank you for your attention and see you tomorrow. Nothing moves. Okay, so yeah, I think thank you. Can you check if the I'm not sure there is here anything. Okay.
¿Alguna pregunta? En Mérida, IBIC, UCB.
No. María, no hay pregunta.
No preguntas. Okay, good. Thank you again. And why? Because they don't move. Huh? That's strange. I don't even show that. Maybe someone else is. Was it understandable?
Yes.
Yeah.
Hard.
Is it hard? Is it hard?
I think that it's very important to know about the equation and automatic things, but it's very hard.
Yeah. So that's what I wanted to give you is the PowerPoint. We have that, and maybe you will not use it now. Time if you are doing such experiment. Time, it's very useful. First course, it's very difficult to get in books.
Yeah.
Actually, you never find them.
Yeah.
So as concentrate on that,
Buenas tardes, aquí la Organización Bolívar. Muchas gracias por su atención. Ya el conferencista terminó.